Okay, so this is the second video in my series on state, describe and explain. We're going to start off with a motion graph. So we've got a graph showing the position of the steel ball that has been projected horizontally, and it shows how it changes with time, and the positions are marked at constant time intervals. Explain how the horizontal motion of the ball shows that air resistance is negligible. So there's a few key points to get in here. The first thing is to recognize that it's traveling at constant velocity because it travels a constant distance of 0.2 meters each unit of time. And then we can use that to explain why the force is negligible. So if velocity is constant, Newton's first law tells us that the resultant force is zero. Air resistance is the only force that can act horizontally, so if resultant force is zero, that must mean air resistance is zero as well. Okay, so that's the horizontal motion. Let's now have a look at explaining the vertical motion. So just like last time, the thing to realize is the vertical distance is increasing every unit of time, so the velocity must be increasing. So then, using Newton's second law, an object can only increase its velocity if there's a resultant force in the same direction of the velocity, which in this case would be the object's weight force, so it's gravity causing it to accelerate, but that's why it's behaving that way. Okay, so for part C, if air resistance were not negligible, describe how this would affect the horizontal motion of the ball. Well, we are now going to have a decreasing velocity in the horizontal direction because there is now a resultant force acting against the motion of the object, which will make it decelerate. And then as for the vertical motion, the acceleration of the object would be smaller as air resistance would act to decrease the resultant force, but air resistance is going to be less than the weight force. So it's still going to have a resultant force downwards, so the object will still accelerate downwards, and it will keep doing that until air resistance is equal to the weight force, which will be then make acceleration zero, and the velocity will be constant. Okay, so moving on to 2. This time we've got a speed versus time graph, and it shows the speed of a parachutist over time, and it does it over the first 20 seconds of the jump. So what he's going to do is he's going to jump out the plane and he's going to wait a period of time before pulling the cord to release the parachute. So you've got 3 sections that we're interested in to start with, A, B, and C. And what we're going to do is explain what the graph shows about those regions. So let's start with A. So we can see that A is a straight line graph. So it's a straight line to start with, which means the acceleration is constant because the acceleration is the gradient of this graph. This will be because the speed is very small, so air resistance is negligible. So the resultant force is pretty much constant because it's just equal to the weight force of the object. That is the part that explains why the graph is this shape. It's the resultant force is constant because air resistance is negligible. In section B, what is happening is the gradient is decreasing, so the acceleration is decreasing. And this is happening because air resistance is getting bigger, because speed is getting bigger. So it's colliding with more air particles every second. And that makes the resultant force smaller, which causes the decreasing acceleration. And then part C, we can see the gradient is almost or approaching zero. Therefore, acceleration must be almost zero. And this will be because the speed is increased even more and air resistance is almost equal to the weight force, so resultant force is almost zero. So now what we're going to do is we're going to use the graph for some calculations. So calculate the maximum deceleration of the parachutist in the region marked D. And we need to show a method that we're using. So the maximum deceleration will be with where the maximum gradient is. So that's what I've done. I've drawn a tangent to the section with the steepest gradient. Then all I'm going to do is find the gradient of that tangent, which you can see I found the coordinates, and then I'm going to do change in y over change in x. That gives us an acceleration of minus 15, which gives us a deceleration of 15 meters per second squared. Next part, use the graph to find the total vertical distance fallen during the first 10 seconds, again showing our method. So you should know the distance travelled is the area under the graph. So I'm going to do this by splitting it up into easy to find shapes to get the area. So we've got 3 triangles, 2 rectangles, and we do need to get very close to the graph so we have a good approximation. And then what you can see on the right hand side is I've calculated the area of each of those sections, added them together, and got the total distance. Now you can do this by counting the squares and adding them up, that's fine, but I prefer using this kind of method. Okay, so during his descent, the parachutist drifts sideways in the wind and hits the ground with a vertical speed of 5 meters per second and a horizontal speed of 3 meters per second. Find the resultant speed with which he hits the ground. So these two are perpendicular, so we're going to use Pythagoras as a method to calculate the resultant. So that comes out as 5.8. Now we want to calculate the angle to the vertical. So let's first represent them using a vector triangle. So it's 5 down, 3 across. We want the angle to the vertical. So I'm going to use tan to solve for theta, which will be 31 degrees. Okay. So third and final question. Most cars manufactured have airbags as a safety feature. In a collision, the airbag inflates automatically to protect the driver as air is released from a compressed air cylinder. Explain why the driver would be less seriously injured in a collision if the airbag inflates than he would be if he was unrestrained. So the key to this question is going to be Newton's second law. So first of all, what does Newton's second law say? Well, it says that the force experienced by an object is equal to its rate of change of momentum. So with or without the airbag, the change in momentum is going to be the same because you're traveling at some speed, then you become stationary. So that's not what's causing this. But the time taken with the airbag will be longer. So the collision with the airbag will be longer because it's compressible than with just a seatbelt with your head smacking into the steering wheel or something. So the consequence of a longer time is the resultant force will be smaller with the airbag, which is why you're going to have smaller injury or reduced injuries because the force is smaller. Okay, so part B. Why is the driver of a car fitted only with seatbelts more likely to be injured than if an airbag was fitted? So this time we're going to ignore the deceleration times and ignore the difference in the materials used. So I've come up with a couple of different things you could use to explain this. So the area of an airbag is much bigger than a seatbelt is, which means the force would be distributed over a much wider part of the body, which will give smaller injuries to each part. That's one way you could argue this. But the other problem with just a seatbelt is the seatbelt is not attached to your head. So there is no force acting to stop your head moving forward, but there is a force acting to stop your body moving forward. So what will happen is, because there's no force on your head will keep going forward, but your body will stay where it is. And so you'll get something we call whiplash, where your head gets thrown forward really quickly and can do a lot of damage. So that's probably the reason they're looking for in this question. Okay, so that finishes this week's State, Describe and Explain. If you have any questions about any of these parts, please do comment and let me know and I'll get back to you. But thank you for taking the time to watch.